Okay, this is the P2 paper from June 2023. It's question number 9, and this is a trig identities and equations question. We've got a function here, an equation here, that we're going to need to rearrange and make look like that quadratic in cos. And then the second part, we're going to basically adapt. Here we've got 2x replacing theta. Try and solve this equation by solving this one, but we'll need to look at the range of values there. Let's jump into it and then you'll see exactly what we've got to do. So the first part is taking this equation here in A and seeing whether we can manipulate it to look like the quadratic in cos. So yeah, let's make a start to it. We've got 3 cos theta, tan theta, tan theta sine theta, plus 3 is equal to 11 minus 5 cos theta. So if I look at where I'm trying to get to, it's just a quadratic in terms of cos. So the first thing I'm going to do is to get rid of my tan theta, because I know the identity that tan is sine over cos. So I'm going to get sine theta over cos theta. Sine theta plus 3 equals 11 minus 5 cos theta. Let's multiply out that bracket, because then the coses will disappear there when I do that. So multiplying out the bracket, I'm going to get 3 sine squared theta plus 9 cos theta is equal to 11 minus 5 cos theta. Sine times sine is sine squared. Those two coses cancel each other out, so we end up with that. Okay, let's get everything over to the left-hand side, and also let's take account of the fact that sine squared can always be changed, because the other thing that we know, let's write it down, is that sine squared theta plus cos squared theta is equal to 1. So sine squared is going to be 1 minus cos squared. So if I put that in, I'm going to get 3 lots of sine squared is 3 lots of 1 minus cos squared theta. Good if I could write properly, plus 9 cos theta, and as I say, also take the 5 cos theta and the 11 over to the other side there. What's that going to give me? 3 minus 3 cos squared theta plus 14 cos theta minus 11 equals 0. And actually, if I take everything back over here, take everything over to that side, we'll get the equation that we're looking for, which is 3 cos squared theta minus 14 cos theta, but plus 8 equals 0. So yeah, that is exactly what we were trying to do here. And now this second part says, can we solve this equation? But if you take a quick look, 2x theta, 2x theta, 2x theta, 2x and theta, everything else is the same there. So when we're looking at trying to solve this equation, we can really solve this equation, but using 2x. Let's explain that to the examiner. So part B, we're going to say, let's start off with that 3 cos 2x. So 3 cos 2x, tan 2x, sine 2x, plus 3 is equal to 11 minus 5 cos 2x. From part A, then, we can say that's the same as 3 cos squared 2x minus 14 cos 2x plus 8 equals 0, and then we can try and solve that equation. Before I do that, I want to just, I always do this right at the start. In the question it says x is between 0 and 360. So when I'm trying to do my solution for this equation in 2x, I'm going to need to go all the way up to values between 0 and 720. Okay, let's actually solve this quadratic then. So if we've got the quadratic, 3 cos squared 2x minus 14 cos 2x plus 8 equals 0. I've got other videos on the channel, if you go and have a look at them, on how to solve quadratics where the value there is greater than 1. Go and have a look at those if you need to. I'm not going to show that here simply because this video would be too long otherwise. This one does factorize to 3 cos 2x minus 2 or cos 2x minus 4 equals 0. So that breaks down into two sets of answers, either 3 cos 2x minus 2 equals 0, so that's cos 2x equals 2/3, or cos 2x minus 4 equals 0, which gives me cos 2x equals 4. That doesn't surprise me at all. They do this quite often. That's not possible, is it? Imagine what cos has to be between 1 and minus 1, so that gives me no solutions, and that's nice because it means I can focus over on this side on just solving this equation. I always do these in the same way. What I do is I say, okay, cos of some acute angle is equal to 2/3. Let's work out what that acute angle is, and that works out to be 48.1 degrees. Remember, we're working in degrees here. So what that means is, I now do my cast diagram, which I say, first of all, if alpha is equal to 48.1, there are these four possibilities where alpha is equal to 48.1. It's the acute angle, it's there, here, here, or here. And what I now do is I say, I'm using my cast diagram, all sine, tan, cos. I would hope that you're familiar with this already. And what does that tell me? It tells me that all the ratios are positive there, sine's positive in here, tan's positive there, cos is positive in there. So if that's true, I'm trying to get cos 2x equals 2/3, which is positive. So where are my two answers going to be? Cos is positive in there, and cos is positive in there. So those are the two lines that represent my solutions, okay, for 2x. 2x is going to be equal to 48.1, which is that angle. It's also going to be this angle, if I keep going all the way round there, which is 360 take away 48.1. That works out to be 311.8 degrees. But then remember what we said up here about when I'm looking for my solutions, I need to, for 2x, go all the way up to 720. So what that means is that as well as that first one here, as well as that angle, what I've also got is the same representation of that angle would be adding 360 on. Well, I'm showing the diagram there, but actually it's much simpler to just say add 360 onto 48.1. So that gives me 408.1. And add 360 onto 311.8. That gives me 671.8. It looks like they're all outside my range, but remember, those are all 2x. So I'm now going to divide those all by half. So divide those all by 2. So if I divide those all by 2, I'll get all my solutions that do fit in between the original range of 0 to 360. I get those four values, 335.9, and everything was to one decimal place in my question. So hopefully that all makes sense for question number 9.